Today I'm going to talk about radical chemistry. Radicals are any atoms or molecules carrying unpaired, at least one unpaired electron. Here there are two types of cleavage of bonds. First is called heterolytic cleavage, as you can see here. So the hydrogen chloride in the aqueous state, the bond between them is broken heterolytically. It's called heterolytic cleavage, and we can use this normal double head arrow. So this dissociation reaction give proton or hydrogen plus and plus chloride anion. So the chloride anion took the two bonding electrons toward itself because it's more electronegative. While in presence of by introducing heat in the gaseous state, HCl can be broken, the bond between them broken equally. It's called homolytic cleavage, to give two radicals, each one carry one dot. This dot is unpaired, or one single unpaired electron, to give hydrogen radical plus chlorine radical. The order of stability of radicals, as can be shown here, tertiary radical is more stable than secondary, than primary, and the least stable is the methyl radicals. Also, the radical that's adjacent to conjugating groups like allylic radical or benzylic radical are much more stable even than tertiary radical, while vinyl radical, alkenyl radical, and phenyl radicals, all of them are unstable. Also here, the radical adjacent to carbonyl group, like electron withdrawing group, or adjacent to nitrile group, also electron withdrawing, or electron donating group like ethoxy, all of them are stabilized by delocalization. Before we start talking about radical chemical reactions, we need to know first what's meant by regioselective reaction, which is the reaction generates predominantly one possible product over others. Also, we need to know that any chemical reaction proceeds through the formation of the most stable intermediate. For example, here, if the reaction goes through the most stable intermediate B, so the product C will be formed. But D is less stable than B, so D will not be formed. And this is regioselective reaction, and the product is a regioselective product. Radical reactions can be classified into 7 types. Let's start with the first one, which is chlorination of alkane. For example, chlorine, when react with cyclohexane in presence of light, will give cyclohexyl chloride plus HCl. All of the mechanisms of radical reaction proceed through 3 steps. First, initiation reaction, and this to generate the radical by introducing heat or light, as we can see in this example, or we can also use initiator reagents such as peroxide or AIPM molecule, as we will see later. Second, propagation step, and in the propagation step it always proceeds through 2 steps or 3 steps, depending on the mechanism, and at the end it will give the radical which will be recirculated to continue the reaction. This is why it's called the chain reaction. For example, here, chlorine radical that's coming from the initiation step abstract the hydrogen radical, which is secondary radical, from cyclohexane to give secondary radical of cyclohexyl, and this radical stabilizes itself by reacting with chlorine molecule to give the product plus the radical that will continue the chain reaction. And at the end, termination reaction, in which all of the radicals react with each other until this has happened after all of the reactants consumed. Chlorine reagent is a very reactive. This can be shown through this exothermic reaction in the propagation step. So the main factors that control the production of the products is the number of substituted hydrogen. Here we have 9 hydrogen primary and 1 hydrogen tertiary. This is why the main product, 63%, is replacing the primary hydrogen to give isobutyl chloride, while only 37% yield for replacing of tertiary hydrogen to give tertiary butyl chloride. While in bromine, the first step of propagation is endothermic, as shown here. So this is why the main factor for the reaction is the stability of intermediate radicals. So the tertiary radical is more stable than primary radical. So bromine is less reactive but more selective, and the yield is 99% for tertiary butyl bromide. Treating alkene with bromine molecule in presence of light or heat can lead to formation of allyl bromide, as you can see here, with the replacement of allylic hydrogen atom with a bromine atom. The mechanism includes the formation of the very stable allylic radical. The addition of bromine should be very slowly and not in excess, otherwise the undesired side product dibromocyclohexane will be formed through the radical addition on the pi bond. To avoid the formation of this side product, NBS or N-bromosuccinamide, this one, can be used instead to produce bromine molecules very slowly in situ or during the reaction. As you can see, the yield is 85% in the first example. In the second example, only the allylic hydrogen that located far from the bulky tertiary butyl it was replaced, and it is less sterically hindered. Tributyl tenhydride can be used to remove various functional groups, including halogens, such as bromine, as in this example, or sulfides, as we will discuss later. So AIBN and tributyl tenhydride used in combination. AIBN, or also called isobutyronitrile, used as an initiator to abstract hydrogen from tributyl 10 to give tributyl 10 radical. And this is the first step of the propagation step. So tributyl 10 radical abstract bromine and they give secondary radical that in turn stabilize itself by reacting with tributyl tenhydride, and it gives the product with the active radical that continues the reaction. The reaction between hexyl iodide and aquilonitrile in presence of tributyl tenhydride and AIBN displayed the addition of hexyl radical here to the beta carbon atom of aquilonitrile to form this new red bond and form the stable radical, this one, next to nitrile group. Then the radical will take or abstract a hydrogen from tributyl tenhydride to give the product. Similarly, carbon-carbon bond formation can happen intramolecular using the same reagent tributyl tenhydride and AIBN as initiator. The mechanism of the reaction is very similar to the others that shown before, but this time tributyl 10 radical will abstract phenyl sulfide, as shown here, to produce a stable radical next to an oxygen atom. You need to notice that the formation of smaller rings is more favorable than larger ones in radical chemistry. In pinnacle reaction, after the carbonyl group, this one, receiving an electron from magnesium metal to form ketyl radical, two of these ketyl radicals conjugated together through magnesium ion and bond formation. Then, in presence of acidic condition, it will form the diol. In case of using titanium chloride, the reaction will not stop at diol, but it will suffer from dehydroxylation to form alkene, and this is called McMurray reaction. The product produced from the reaction of HBr with isobutene depend on the condition of the reaction. If we don't use any peroxide, or there is no any peroxide, so the reaction will proceed through the formation of tertiary carbocation to give tertiary butyl bromide, which obey Markovnikov's rule. And this reaction is electrophilic addition reaction. While in presence of peroxide, so the bromine radical will react first with the primary carbon of the alkene or terminal carbon of alkene to give tertiary radical, then abstract a hydrogen to give isobutyl bromide, and this product doesn't obey Markovnikov's rule. At the end, please try to answer these practice questions. Thank you.